So in our previous videos, we dealt basically on working with complex numbers in the format of Cartesian plan, where we say z is equals to, let's say, a plus bi. Okay, now we want to look at complex number in the form, in polar form. Okay, in polar form. Now in polar form, we can rewrite the complex number as z is equal to r into cos theta plus I sine theta. Now, what is our r and what is our theta? Okay, so r in this case is tagged the modulus, and the theta is the angle between the positive x-axis and the complex number itself. So let's explain this further. Given a plus bi, z is equals to a plus bi. Okay, now the first thing we will do is to draw an Argand diagram for this illustration. Remember, we did Argand diagram in the first video, so you might have to go back there for more understanding on it. Now in an Argand diagram, to recap, the positive x-axis stands for the real axis, okay, and the vertical axis stands for the imaginary axis. Okay, so let's say we have plus a here and we have minus a here, we have plus b here and also have minus b here. Okay, now in that case, let's move this. In that case, we can see that we have, in this complex number, we have it to be positive a and positive b, so therefore we are having it in this space. So this is our z. Okay, I'll call this bi, or we can leave it as b. Okay, now if that is the case, then we can bring out this alone itself. Okay, so let's label that and let's draw it again, and we will realize that the distance between here and here is a, and the distance here and here is b. Now the angle theta is this thing. Remember, it's right angle. So our r, which is the modulus, okay, well, we talk about it like in Pythagoras theorem. You can say that our r square is equals to the sum of the squares of the opposites and the adjacent. Okay, so r can be the square root of a squared plus b squared. And if you remember, so you know that sine is opposite over hypotenuse, cos or cosine is adjacent over hypotenuse, and tan is opposite over adjacent. Now, considering this angle now, the opposite here is b, okay, and this is the adjacent. Okay, so in that case, we can henceforth say that tan theta is equal the opposite, okay, which is b, over the adjacent, which is a. So our theta will be arctan b over a. So with this, we can quickly pick an example on to convert polar form or Cartesian form to polar form. So let's emphasize that before we go on into the theorems or principles. So let's take for instance we're given z is equals to 4 plus 3i. Okay, now the first thing to do is to sketch it on an Argand diagram. Now sketching it on an Argand diagram, we have it to be this will be 4, okay, and this can be 3. Remember, this is the imaginary axis and this is the real axis, right? So in that case we can have it to be this, or z, okay, or r as the case may be, and this will be our angle theta. Remember that the distance, noting that the distance between here and here is 3, and the distance between here and here is 4. So easily we can bring out the triangle, okay, bringing out the triangle as the case may be, we have it to be 4, 3, r, and theta. So after that is done, our r, according to Pythagoras theorem, will be the square root of 3 squared plus 4 squared, or 4 squared plus 3 squared, as the case may be, which will be equal to the square root of 9 plus 16. R will be the square root of 25. So R is equals to 5. And in this case, our theta, okay, now we can see that the side facing angle theta is always called the opposite. So 3 is the opposite, the other side is called the adjacent. Okay, so since tan theta is opposite over adjacent, the opposite is 3 and the adjacent is 4. So tan theta is equals to 3 over 4. Then theta will be arctan of 3 over 4. And arctan of 3 over 4 in degrees, using my calculator here, is 36, okay, 0.87 degrees. Now, after knowing our r and knowing our theta, I will recall that the actual question is z is equals to 4 plus 3i. 4 plus 3i. Our r is equals to 5. Our theta is equals to 36.87 degrees. Right? And in polar form, representation in polar form, we have it to be z is equals to r into cos theta plus I sin theta. Okay? In this case, then we can say that our z is equal, the r is 5 into cos theta, the theta is 36.8687 plus I sine 36.87 degrees. Now, what we have here is the polar representation or the polar form of this vector, of this complex number here. Okay, so now if this is equal to this, okay, we have been able to transform from Cartesian to polar form. How then can we transform from polar form back to Cartesian? Okay, now let's look at z is equals to 5 cos 36.87 degrees plus I sine 36.87 degrees. Now we want to convert back to polar form, to Cartesian form. So this is 5. Now cos 36.87 degrees is 4 over 5 plus I, and sine 36.87 degrees will be 3 over 5. Okay, now opening the bracket with 5, we have it to be what? 4 plus 3i. So this is simple, we have been able to transform from Cartesian, okay, from Cartesian to polar, and this is moving from polar to Cartesian. So this is a simple conversion from of complex number from Cartesian form to polar form. Now let's go a bit deeper. There is something they call argument, argument Z, argument Z. Okay, in some case is the same thing as theta, so we call theta the argument of the complex number. Okay, theta is the argument of the complex number. And let's take a bit diversion. If we go from this direction, this is the positive x, okay, this is the negative x, this is the positive y, and this is the negative y. Now the angle is being counted, argument z is being counted, is being measured from the positive x in the anti-clockwise direction. Okay, so we can call here as a measurement of argument z. Okay, now in that case, let's take a bit analysis, because if we have Cartesian planes or polar form in an Argand diagram, if we have it in this format 1, 2, 3, and 4, let's call this one, we can call this one a plus bi, okay, and we can call this guy minus a plus bi, and we can also call this guy, okay, minus a minus bi, and finally this can be called a minus bi. And let's explain. Positive real, negative real, positive imaginary, and negative imaginary. Now if you look at a plus bi, okay, that means it has a positive real number and a positive imaginary number. If you look at minus a plus bi, it has negative real number as we have here, and it has positive imaginary number. And if you have minus a minus bi, negative real number, and this is a negative imaginary number as we have here. And the same applies for this, which is as a positive real number and negative imaginary number. So we will be considering these individuals a bit by bit so that we can come to a conclusion on how to convert from Cartesian plane to polar form, to polar form, ensuring that the arguments are not mistaken for each other. So let's start from a plus bi. In a plus bi, the first thing to do is to draw the Argand diagram. Okay, the first thing to do is to draw the Argand diagram. So drawing the Argand diagram, we have this. Now a means it has positive real number, and positive imaginary number. Okay, so in that case we have positive real and positive imaginary number. So definitely the complex number is within this quadrant. So in that case we have it to be this, right? So we can call this a and we can call this b. and this our theta, which is at right angle. Okay, so we can bring out our diagram or our triangle and simplify it here. Okay, you can repeat it here with angle theta, with A and B, and our modulus R. In this case, angle theta is facing sine B. Okay, so we take that B is opposite to angle theta. So B is the opposite and A is the adjacent. This is the same as what we've done earlier when we started with. Okay, now therefore can I have that our R is equal, or R squared according to Pythagoras theorem is A squared plus B squared. So our modulus is the square root of A squared plus B squared. And using tan theta, which is equals to the opposite over adjacent, and our opposite is B and our adjacent is A, as we have seen here. B is equals to opposite, A is equals to adjacent. So our theta is equals to B, or arctan B over A. Now, if our theta is equals to arctan B over A, what will be our argument Z? Now, let's come back to argument Z here. Now, the measurement of argument Z, as we have seen here, the measurement of argument Z is from the positive x-axis to where the complex number is from. Okay, so we have our we have our complex number here at this position, and this is our theta. Okay, and argument Z is start reading from positive x-axis, or let's say positive real axis. Okay, from this let's say positive x-axis. Now, if argument Z is reading in that direction, and we can see up to the point that is being measured, so this is our argument Z. Since theta is the argument of the complex number, so in this case our argument Z is equal to theta, right? Because the angle here is equal to the angle here. Angle theta is equal to argument Z. Now, this is one. Let us now consider, what if it is in this quadrant? Okay, if it is in this quadrant, that means we are going to have, okay, let's analyze it a bit before we move any further. This will have a positive x, this has positive real axis and positive imaginary axis. This has positive imaginary axis. Okay, let's swap this. Positive imaginary, positive real, and this has a negative real number. Okay, negative real, positive real, and negative real, negative imaginary. Sorry. Now, if we look at this quadrant, what will we have? It will have positive real, okay, and also it will have a negative imaginary number, and this will have a negative real number and a negative imaginary number. Okay, now in that case, let us look at, we have looked at this. Okay, we've established this, and now let us go on and establish this. This stands, we can assume this to be A plus BI, and we can take this to be a. The real number is negative, the imaginary is positive, that's minus a plus bi. Here the real number is positive a, the imaginary number is negative, that's a minus bi. Here the real number, finally here the real number is negative minus a, the imaginary is also negative minus bi. So we have established a plus bi. Now we will take minus a plus bi, minus a minus bi, and a minus bi bit by bit. Let's go with minus a plus bi, minus a plus bi. The first thing we did here was to draw the Argand diagram. Okay, now let's draw the Argand diagram here. Remember that minus a has negative real and it has positive imaginary. So this is positive real, negative real, and this is positive imaginary, and this is negative imaginary. So in that case, what we are looking at is here minus a and here b. So we have our Argand diagram z or r as the case may be, and this will be our angle theta. So the next thing to do is to bring out the triangle. Okay, you can repeat it down here, and angle theta, and this is our r. So as usual, we know that the distance between here and here is b, and the distance between here and here is a. So in essence, we're saying this is b and this is a. So if that is b and this is a, the angle facing it, okay, the side facing the angle is b, so b is the opposite and a is the adjacent. So we come to the conclusion that r, as we know, is the square root of a squared plus b squared, and tan theta is equal to opposite over adjacent. So theta and opposite is b and adjacent is a. So tan theta is equal to b over a. Therefore theta is equal to arctan b over a. If theta is arctan b over a, what then is argument z? In the first instance, we said argument z is equal to theta. Okay. Now, what happens to argument z? Is it changing here or is it going to remain the same? Let's take a look again at the Argand diagram. This is it. Okay. And our angle theta. Recall that argument z starts counting from the positive x-axis or the positive real axis. So our argument z starts counting from here to where the complex number is. So this is argument z. Okay. Now, so perform a little bit of trigonometry here. We know that the angle on a straight line is 180 degrees, right? So therefore, we know that our argument z plus theta is equal to 180 degrees. So therefore, our argument z is equal to 180 degrees minus theta. So with that being said, we can come to a conclusion that our argument z is 180 degrees minus theta. Okay. Now that we have established a plus bi, we have established minus a plus bi. Let us go into minus a minus bi. Minus a minus bi. Now in minus a minus bi, we can see that we have a positive real and we have a negative real part and we have a negative imaginary part. So drawing the Argand diagram, this is the positive real and this is the positive imaginary. This is the negative real, and finally this is the negative imaginary part. So it will be minus a minus bi. Okay, so the normal Argand diagram will look this way. Good. With our angle theta to the horizontal. So the next thing to do is to bring out the triangle. Okay, so bringing out the triangle, we have this. At right angle theta, the distance from here to here is b, and the distance from here to here is a. So therefore, this is b and this is a. The side facing angle theta is b. So b is opposite and the other is adjacent. So being established, we can now evaluate our R, where we know that our R is like hypotenuse. So our R is the square root of a squared plus b squared, and our theta, or we say tan theta, is equals to opposite over adjacent, and opposite in this case is b over adjacent, which is a. So theta is equals to arctan b over a. Now if theta is arctan b over a, what is our argument z? Okay, what is our argument z? So having done that, let's go back to our Argand diagram with the complex number here, with angle theta here. Okay, now argument z is start counting from the positive real axis, right, or positive x axis. So argument z start counting from here up and in the anti-clockwise direction up to when the z, up to where it reaches the complex number. So this is our argument z. Okay, now in this case, what is our argument z? We can see, we know that the angle on the straight line is 180 degrees, right? So that means our argument z is equal to 180 degree plus the remaining angle here, theta. Okay, so after that being established, we can come and say our argument z is 180 degrees plus theta. Okay, now with that being done, we have talked on a plus bi, we have talked on minus a plus bi, we have talked on minus a minus bi, and finally let's do a minus bi. A minus bi. In a minus bi, we have a positive real and we have a negative imaginary. Okay, now drawing the Argand diagram, positive real, positive imaginary, negative imaginary, and negative real. So we have it to be a and we have this to be minus b, and it comes this way. And angle theta to the horizontal is, knowing that the distance from here to here is b and the distance from here to here is a. So having done that, we can easily bring out our triangle affected. so that we can understand the principle, understand how to calculate the modulus and also the angle theta. So bringing out the triangle, we have this, okay, where this is our angle theta. The answer is B, this is A, this is R. This is right angle. Now, the side facing angle theta is the opposite, so B is the opposite and A is the adjacent. So in response, our R is equal to the square root of A squared plus B squared according to Pythagoras theorem, and tan theta, which is opposite over adjacent according to SOHCAHTOA, and the opposite is B and the adjacent is A. So therefore our theta will be equals to arctan B over A. Now if theta is arctan B over A, what is the argument Z in this case? We have noticed that the theta keeps on being the same format, arctan B over A, arctan B over A, and R being the same thing as square root of A squared, okay, plus B squared, right? And theta keeps remaining the same in all scenarios. So let's take a look at the Argand diagram so that we can evaluate our argument Z. Theta, and this is our Z. Z. So we know that argument Z starts counting from the positive x-axis, from this axis. Okay, so we count from here to here. Okay, so this is argument Z. Now looking at this now, we can see that this looks like angle at the point according to trigonometry, and angle at the point is 360 degrees, right? So we are saying that argument Z plus angle theta is equal to 360 degrees. So argument Z is equal to 360 degrees minus theta. So we can come back here and effect the change. Say this is 360 degrees minus theta. Now we have done for the fourth quadrant. Now we want to bring them all down into a single, to summarize them down into one single page. Now in that case, we have a big quadrant, and we can label each quadrant. We can call this A plus BI, and we can call this minus A plus BI. Okay, this can be called minus A minus BI, like we solved before, and definitely this is minus of A minus BI. Now having done that, we can see that this one has a positive real part and as well a positive real part. This one has a negative real part and a positive imaginary part. This has a negative real part and as well as a negative imaginary part. This one has, and finally, there's a positive real part and a negative imaginary part. Okay, so we can now go back to them one by one. Let's start with A plus BI. Let's come back here. A plus BI. Looking at A plus BI, our R remains the same and our theta remains the same. But what is our argument Z? and what does the diagram look like. Okay, so these are the things we'll be affecting. We can see that our argument z, first of all, is theta. So we can come down here and say that our argument z is equals to theta. Our r is equal to the square root of a squared plus b squared, and our theta is arctan, okay, b over a. Good. Now, having that done, let's go to a minus a plus bi, minus a plus bi, minus a plus bi. Our r is square root of a squared plus b squared. Our theta is arctan b over a. Our argument z is 180 degrees minus theta. Okay, those are the informations we need. Now let's go back. Our argument z, most importantly, is 180 degrees minus theta. Our r is square root of a squared plus b squared. Our theta is arctan b over a. Okay, now let's go to minus a minus bi. Minus a minus bi, we have that our r is square root of a squared plus b squared. Our theta is arctan b over a, and our argument z is 180 degrees plus theta. So come here and effect it. Our argument z is 180 degrees plus theta. Our r is square root of a squared plus b squared, and our theta is arctan b over a. And finally, we want to consider a minus bi. A minus bi. Our r is square root of a squared plus b squared. Our theta is arctan b over a, and our argument z is 360 degrees minus theta. So argument z is 360 degrees minus theta. Our r is the square root of a squared plus b squared, and our theta is arctan b over a. Now this will be the basis of our conversion mode from Cartesian plane to polar form. So in that case, let us remind ourselves of Cartesian plane and polar form format. In Cartesian plane, in Cartesian format, we have that our z is equals to a plus bi, as the case may be. Then in polar form, our z is equals to r cos theta plus I sine theta. Okay, now as the case may be, the theta here will begin to change, and we can also write it as r argument z. Okay, so let's take a quick recap on what we've done so far. We dealt with a plus bi. We dealt with a minus a plus bi. We dealt with minus a minus bi, and finally a minus bi. And we saw how their arguments z are changing, okay, from theta to 180 minus theta, okay, to 180 plus theta to 360 minus theta, depending on the quadrants at which they are. So in our next video, we will take questions on how to convert from Cartesian form to polar form, and we will also convert from polar form to Cartesian form.